Welcome to The Explainer. Today we're diving into a really radical idea, one that could totally reshape the future of information and, maybe even push us beyond the age of electronics. We're talking about a future where computing is as natural as light itself. So yeah, let's get right into it. Okay, so to really get where we're going, we first have to talk about the wall that we're all about to hit. For decades, right, we've lived by Moore's law. Computers just kept getting faster and faster exponentially. But that incredible ride, well, it's slowing down. We're running up against a fundamental physical limit. So what's the big bottleneck here? Well, on one hand, you've got our current electronics. We're literally pushing electrons through these teeny tiny circuits, and that generates a ton of heat. And we're hitting a wall with how small we can make them. Plus, we're forced to translate the beautiful richness of reality into this rigid, kind of clunky binary code of just zeros and ones. But then, what if we use light instead? Photons have zero resistance, they move at the ultimate speed limit, and they can represent a whole spectrum of information, not just two states. This is the incredible promise of photonics. And this all leads to a really fascinating question. What if, instead of forcing nature to speak our rigid digital language, what if we build computers that could speak the native language of physics itself? This is the absolute core concept of what's being called light and energy computing. It's a system where information isn't some abstract thing. The information is the energy. So forget bits and bytes for a second. Instead, I want you to picture information as a physical pattern, kind of like a complex ripple spreading across a pond. And this quote, man, it just nails it. The field isn't just carrying the data from point A to point B. The field is the computer. What this means is that computation doesn't have to be this abstract symbolic process happening on a silicon chip. It can be a natural physical transformation that we can just directly read and interpret. It's a huge shift in thinking. Okay, I know. The concept is pretty out there and fascinating. But how would you actually build a machine like this? Well, the proposed design is surprisingly elegant, and you can break it down into a 4-layer architecture. Let's just walk through that pond analogy again. So first, you've got the EM field. Think of that as our pond, holding all these complex ripple patterns. Second, the emitter, which is basically a laser, acts like a super high-speed camera. It takes a perfect snapshot of those ripples and encodes them into a beam of light. Third, the reader analyzes that photo, measuring every single tiny detail of the light's pattern. And then finally, the converter interprets that whole analysis and tells you what the ripples actually mean, giving you a useful output. Now you might be thinking, hey, this sounds a little bit like optical computing or maybe even quantum computing. And you're not wrong. It's definitely related, but it's actually a totally distinct new branch on the big tree of science. Let's take a look at where it fits in the grand story. See, this idea didn't just pop out of nowhere. It's really standing on the shoulders of giants. You've got Newton way back showing us that light could be structured. Then Maxwell comes along and reveals it's all part of this bigger electromagnetic field. Fast forward to Turing, who gives us the theory for the abstract computers we use today. And now, with the invention of lasers, we finally have the tools to bring all these ideas together, to build a computer that's truly physical, not just symbolic. And this table is where you can really see the difference. Classical optical computing, that's just swapping electrons for photons but keeping the same old binary logic. Quantum uses the wild properties of qubits. But look at the core principle for light and energy computing. The data is native to the field, and this is the absolute key difference. For every other computer, logic is the foundation. Here, logic is the final output. It's just an interpretation of a natural physical process. Right, so that fundamental difference is exactly what makes this whole concept so incredibly powerful. I mean, if we can actually build it, the potential applications could launch us into a whole new era of information processing, the post-electronic age. Just imagine it. AI models that make decisions literally at the speed of light, or advanced sensors that can read the environment, whether for medical diagnostics or searching for resources, in a way that's completely impossible with today's electronics. We could even develop these amazing hybrid machines that bridge the quantum and classical worlds, or create secure communication channels that are fundamentally harder to intercept. The possibilities are just staggering. Ultimately, what we're really talking about here is a fundamental shift in philosophy. The goal is to stop trying to cram information into electrons and bits, and instead to build a computational architecture that is native to the physics of the universe. We're moving computation closer to nature itself. And that leaves us with one last, kind of provocative thought. For all of our incredible digital achievements, We've really just been forcing the world into this tiny box of zeros and ones. But what if we could build technology that understands the world on its own terms? What if computation could be as natural, as elegant, and as infinitely complex as a ripple in a field?